discussing polynomial functions and their models. Recall from the past that a polynomial function, the degree of it is the largest exponent involved. The degree of a model of a polynomial function is one more than the number of turning points in the graph. And when you are given a polynomial function, the graph will have at least one less turning point than the degree. Give you a few minutes to write those three things down, because that is what encircles our entire lesson. Here are the different functions. Recall a constant function was f of x equals a, and it was a horizontal line. We also studied a linear function, f of x equals ax plus b, and it was a slanted line. As we move into the polynomial, the quadratic function was f of x equals ax squared plus bx plus c, and it gave us the parabola. Notice the end behavior of the parabola. Let me try some axes here. That as x gets negative, the function gets positive. As x gets positive, the function gets positive. So no matter what, on a quadratic, the end behavior will be the same. Next is our cubic function, f of x equals ax cubed plus bx squared plus cx plus d, and it makes this S shape. Notice my end behavior. When x gets negative, my graph's y values get negative. When x gets positive, my y values also get positive. The end behaviors are the opposite of each other. So in a quartic function, f of x equals ax to the fourth plus bx cubed plus bx squared plus dx plus e. And it is similar to a parabola. It is just flattened out a little more on the bottom, or it can make this W form. And the end behavior again, as x is negative, my y's are positive. As this x is positive, my y's still remain positive. Likewise on the W, as this x is negative, it gets bigger. And as the x gets positive, it also increases on the y's. So it's still the same end behavior on both sides of the graph. And the last one we're going to look at here is the quintic, which is the fifth power, ax to the fifth plus bx to the fourth plus cx cubed plus dx squared plus dx plus f. And as you notice, I have 1, 2, 3, 4 turning points, and as previously stated, that means my degree should be to the fifth power. And notice it acts similar to the cubic. As x gets more negative, my y's are getting negative. As x gets positive, my y's are getting positive. Opposite end behaviors. A function is called an even function if the end behaviors are both rising or both falling. A function is called an odd if both the end behaviors are the opposite of each other. not to be confused with the degree. An even degree function, not just called an even function, but an even degree function has positive leading coefficient A when both n behaviors rise. And it's negative leading coefficient when both n behaviors fall. That is how you would know if it's a positive A or a negative A, positive rises, negative falls. So on an odd function, positive happens when x gets negative, the y's get negative. As x gets positive, the y's get positive. It will have a negative A leading coefficient when x gets negative, that the y's get positive, or when x gets positive, the y's get negative. When it does the opposite, it has a negative leading coefficient. So let's take a look at some. First in each of these, state the leading coefficient and what degree it is, then describe the end behaviors. So in this first problem, the leading coefficient is LC, -1. Or actually, let's call it A. A is -1. The degree is 2, the exponent. Now the end behavior. As x gets negative, what happens to y? If it's a square and the leading coefficient is negative, that tells you it should be a parabola like this. So as x gets negative, y gets negative. As x gets positive, y also gets negative. On an even degree function, the end behavior must be the same. And since it is a negative coefficient, that tells you they will open down, and behaviors will be down. Okay, let's try this one. F of x equals x to the 7 minus 3x cubed plus 2x. First of all, A, leading coefficient, is 1, and the degree is 7. That is an odd number, so it is an odd function, degree function. So as x gets negative, and it's a positive A, f of x should get negative. As x gets positive, y should get positive. And our last function, f of x equals 4 plus 2x minus 3x cubed. First of all, A is, careful, -3, and the degree is 3. The highest exponent gives you the degree, and the leading coefficient follows with that exponent. So, since it is an odd degree, and it is a negative leading coefficient, it will be the opposite of how it begins. So as x heads towards negative, f of x will head towards positive infinity. And as x gets more positive, y will get more negative. All right. How many turning points? What is the minimum degree possible? is the leading coefficient positive or negative? Match the equation, and then estimate your intercepts, local extrema and absolute extrema. All right, let's do all of this, and then you can come up and match. How many turning points in this graph? 1, 2, 3. 3 turning points. What's the minimum degree possible then? 1 more degree than turning points, so 4th degree. Will the leading coefficient be positive or negative? Since it is a 4th degree polynomial, and they both open down, it would have to be a negative leading coefficient. And let's estimate our x-intercept. X equals about negative 1.4 and about 1.4. Local extrema. Remember, local are all low points and high points. Absolute are the lowest and the highest. So I have a local maximum at -1 and +1. So local max, -1, 1 at 1, so that's a y value. And I have a local min at 0. I have an absolute max, still at the y value of 1, and I have the absolute min, it never ends, so I have none. Okay. Second one has 1, 2 turning points. So the best degree would be 3rd degree. Leading coefficient. X is negative, y's are negative. So it must be a positive coefficient because it matches the domains. Positive, negative. And the x-intercept, I have 1 at approximately 1.2. Local extrema, local max. Let's see, here would be 1 at about negative 3.9. And local min at -4. And absolute max, none, because it never reaches the max, and absolute min is also none. In this graph, I have 1, 2 turning points. Maximum degree. Could be cubic. Leading coefficient. Negative, negative, so it'll be positive. And x-intercept about negative 0.9, 1, and 2.7. Local max at about 6.9. Local min at -3. Absolute max, none. Absolute min, none. and match. Actually, you won't be able to do that on the video. So we said this needs to be a 4th degree. So we would have to take this one. This one, we said, has to be 3rd degree positive. This one looks the same, but one of them is a 5th degree. Okay. I think we made a mistake right here. This leading coefficient, since it goes negative is positive, must be a negative leading coefficient, opposite of what the domain does. So negative leading coefficient, positive leading coefficient. Let's see. That would have to be this one. Now this has a 5th degree. We could go higher than 3, and we're going to have to in this case. So you see how all these will work? Now we want to sketch the graphs. A degree of 2 with a turning point of -1, 2. So let's plot that turning point, -1, 2. Passing through -3, 4. I'm going to change the color of my passing through points. And 1, 4. So if it is a degree of 2, I must have how many turning points? 1 turning point. So it should be parabolic. That would be my graph. This one asks for a degree of 5. It's an odd function with 5 intercepts and a negative leading coefficient. So negative is a degree of 5, negative leading coefficient means up and then down in the end. 5 intercepts. So let's just cross this x-axis 5 times. So 1, 2, 3, 4, 1, 2, 3, 4, 5. We got too many on there. 1, 2, 3, 4, 5. Okay, here would be using. Estimate the turning point and then interpret each one. Here is a turning point, here is a turning point, and here is a turning point. So let's estimate. This looks like 1.5, 3.6. This one looks like 1.3. And this one looks like 4.5, 3.6. And if I have to interpret those, this is the working out runner's distance from the starting line. So when the runner was 1.5 minutes into the workout, he or she was 3.6 times 100, so 3,600 360 meters, I take 3.6 times 100, that's moved two places. 360 meters from the start. After 3 minutes, he or she was 130 meters from the start. And finally, after 4.5 minutes, he or she was again 3.6, 350 meters from the start. It should make sense on a circular track. There are your problems. You can begin